Alrighty. Good to, I guess I'm not seeing you, but hey, you're seeing me. So, um, let's get this started. So, there is a new Discord channel. So, ask away your questions there. Whatever you want to start with, however we can help, because I assume this is your last exam. So, anyone want to start us off? Any questions? Anything we should do? I can hang around here for a while. I'm, in the void. So let's see. Could we review the 2024 IO bound question? Question 20. Which one was that? So yeah, preparation wise, I do have the 2024 fall final blank. If we want to go through that, the question, IO bound question, 2024. I assume 2024 winter ECE353. All right, let's see what that says. Do 2024, this course, I assume, final ed. All right, so question something. I do not see said question. There's page replacement. So which question are you talking about? The 2024 winter ECE353 is not there. Let's see. Maybe it is 344. 344. No, I have that one pulled up. I have no idea which one that is. Final. Am I blind? Question 37 to 39 is... oh, okay. Someone said IO bound question. That's the file system question. Okay. File system question's different. So, let us go back to it then. So this is winter. Okay, let's... Okay, so tablet. So we're assuming, I'm assuming this question, right? Is this the right question? No, not the right question. All right, anyways, so the question is, I'll just pull it up here. So it's another file system question. So the question says, we have a file system. Let's see here, file system. And in this, it states we have a block size of 4096. I always write it in powers of 2 just in case it's relevant. Pointer size is 4 bytes. And inode size is 128 bytes. Then inodes have their usual 12 direct pointers, one double indirect, one triple. Analyze the output of ls. That shows you the inode numbers and everything. Output format includes inodes in the first column, which I included just in case. So, question is, so we do ls, and it looks something like this. So there's our inode column. We have 28, 19, 20, 20, 22, 26, and that, oops, that looks atrocious. Let me rewrite the 20s. So we have inode 20, 20, and then the files, well, let's just put the size. It's the other relevant column. Size is 4096, 4096, 100, 100. Of course, they have to be the same. 1 and 5000. And this should actually be 22. And then the other column is just the name of said file. So we've dot, 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 and then we also have A, B, and then we have C to B, indicating that it is indeed a symlink, and we have file E. So first question says, when editing file C, which inode's contents are modified? So when we modify C, right, it is a soft link. So 22, hopefully you've done labs, you have to have done lab 6 or attempted it by now. So for the symlink, the name that C refers to, which is B, is stored itself on inode 22. You can think of it as just string to string whenever, or name to name for a symbolic link whenever we're trying to edit the file. So that would redirect us, if we try and access file C, it would direct us to B, and B, hey, that's a regular file. It's a hard link, so the inode is the one we would modify. So it is 20. Then the next question says, possible to store all the inodes associated with directory in a single block, provide. So you just keep track of how many inodes you can store on each block. 128 is 2 to the 7, so in this case you can store 2 to the 5 on each block. Inodes, they start at inode 1, so the first inode block would be 1 to 32. I also did the inode numbers in a way where if you're off by 1, didn't matter. And then determine the number of data blocks that file E will occupy. So in this case, we know that, hey, for our inode, right, our inode, it would have some space for direct blocks, and that's where the data would. So the size of the file here, if it's just a regular file, that's how many bytes of data it needs. So you can see from this, if we only had one block, our block size is 4096, wouldn't quite fit on a block. So we would have block 0 of that file. It would be full. It would contain 4096 bytes of actual data we need for that file. And then it would need a block 1, which the maximum size would be 4096. But to store the contents of this file, it only needs to use, 5000 minus 4096 bytes, because that's how many bytes are covered in that block. So this, you can either do the math, which is 904, or, you can use your calculator. So this block would have 904 bytes of that file actually being used. The rest of it would be internal fragmentation, because we're only dealing with blocks at a time. So we would need 2 blocks to store the contents of this file. So hopefully everyone's good with that. And then calculate the number of bytes lost due to internal fragmentation for file E. So it's exactly what we just kind of said here. So we've 4096 bytes of, that's the size of the block, minus however many bytes we're actually using for data, because that's useful information. So minus 904. So the total loss due to internal fragmentation is just this number. On the exam, I don't even care if you give me the final number. As long as you have this calculation, you're fine. But if you want to do this calculation, it is 3,192. And then here's the rest of the question. Yeah, so that one, the rest of the question is like, yeah, we also have the number of links here. So the number of links here, this one was kind of tricky. So there's 2 to dot, 5 to dot dot. There'd have to be 2 to A, 2 to B, 1 to C, and 1 to E, I guess. So one of the questions says, hey, how many directories are contained within the parent directory represented by inode 19? Describe what they all are. So somewhere there has to be, there's a link between dot dot and dot, right? So let's just give this directory a name. So let's just say inode 19. So we can say on inode 19, inode 19, it's a directory. So let's just give it a name for, I don't know, for fun. Let's just call it parent. So some entries that would have to be in inode 19, there'd be some real name for our directory represented by inode, in this case 28, because that is dot. So let's just say it would be, name D1, 28. And then inside of 28 here, right, it's referred to in 2 places. It's referred to as its name D1 in the parent directory, which is represented by inode 19. I just gave it a name parent. We don't actually know the name. There's no way to figure it out. So I just made something up. And then this would be our 2 links here. So it would be dot in stored, as one of the entries in inode 28 itself. And then it would also be in the parent directory given a name. So 28. So that would be how we got our 2 links here, all highlighted in yellow. So here, right, for the parent directory, this is one of the links in my D1 directory. And it turns out, well, this is going to be exactly the same as arguing about the number of links in the current D1 directory. Is just one level up. So in that parent directory, it would have an entry for dot, and that would be itself, so 19. And then it would be given a name somewhere. It would have a parent, right? So it would also have a parent dot dot. I don't know. I have no idea what it is. I'll just call it X. So on inode X, this parent directory would be given a name as well, right? It would be given a name, and it would be inode 19. So it would need to be there, otherwise it wouldn't be connected, and it would not be a valid file system. So this would be another link here for the parent directory. So turns out that every time I make a new directory in the parent directory, I'm going to increase the number of links by 1, because every time I create a new one, it's going to have an entry of dot dot, which points back to inode 19. So if I know the number is 5, well, I know that there is some other entries here, because every single other entry here, so let's just call them D1, or sorry, D2, which would be, I don't know, inode Y, and D3, which would be inode Z. Well, on those, inode Y and inode Z, well, there would also be an entry of dot dot to inode 19, just like there is in my current directory that I just randomly called D1. So it would look like that. So that would get us our 5 other, well, that's the only number that would make sense to get us our number. So in green, it's everything that's highlighted there. So it means that this parent directory would have to have 3 directories within it, because it would have its name from its parent, its dot in itself, that would be 2 links, and then every time there's a directory created in it, it would have a dot dot entry pointing to it. So that gives us our number of 5. All right, so everyone good with that one? And then, yeah, so now the one I actually had set up. So go back. Oh, okay, I already had it pulled up. Perfect. Whoops, that's the wrong thing. All right, so this question. So this is, yeah, most people just want to go over file system questions. And then for the term test 2, threads question, I updated the solution, so you should refresh it. And if the solution was confusing, I just accidentally omitted something. So have a look at that, and if it's still confusing, I will go over it. So let's do the other file system question as well. So let's look at this. So consider output from running ls-li. So this gives us our inode number here. And this is the number of links. This is the size. And then these are our names. So there's 2 symlinks here, right? So there's 1 symlink, 2 symlinks. So first question says, how many bytes are lost due to internal fragmentation for regular files in the output? So first one would be, hey, what's a regular file? So in this case, A and B are just regular files. They're not symlinks, and we have no directories in here or anything like that. So we have to calculate the internal fragmentation for A and B.txt. So it says here our block size is 4096. So for file A, what's lost is 4096 because it would have to occupy a block minus 96. So it has 4000 bytes lost due to internal fragmentation. And for B.txt, well, it also takes a block, and it needs 4000 bytes. So 96 bytes are lost due to internal fragmentation for that. And in total, we just add those numbers together, which is 4096. All right, next one. How many IO blocks are needed to store the content of c.txt? This is the tricky one to make sure you did lab 6. So there is that optimization, right? If it's a symlink and it's less than the total size of the pointers on the inode, typically 60 bytes, the content of the symlink or the name it refers to will be stored using that space for the pointers. That was an optimization that happened in lab 6. So this would just be a big fat 0. So next one is assume the user runs cat d.txt. Assuming nothing is cached, how many IO blocks need to be read from disk? Ignore reads to the directory. Describe the order of block reads and what they contain. So in this case, we would have to read inodes, right? So we read inode 128 because we have to know, hey, well, if they use cat d.txt, well, ignoring the directory lookup because it would need to look up d.txt to find what inode it refers to. In this case, it refers to inode 128. So we would read inode 28. It would figure out that, hey, that is a symlink. Read the contents of it. Doesn't have to read an IO block because the contents are already stored on the inode itself, so we don't have to do anything with that. So that says, hey, refer to c.txt in this case. Oh, okay, well, ignoring the directory read, so I'd have to look up what inode c.txt refers to. It's inode 64. I'm ignoring that lookup because that's what the question said. So I'd have to read that inode. So I'd have to read inode 64. After I read 64, again, I don't have to read data block. The contents are stored on the inode itself. That would give me a.txt. So I would have to look up what inode a.txt refers to. So in this case, it refers to inode 31. So I would read inode 31. And then that would actually tell me where all the data is. So after that, in this case, it only stores one block. That's it. So it would read direct pointer 0 on well, it would read that block. So the direct pointer 0, the first one, would refer to a block, so I'd have to read that block on inode 31. So whatever data block that is, I read it, boom, that's it. So that is 1, 2, 3, 4. And to not carry errors, we made it that if you answered this wrong, so if you assumed the inode was actually stored using a data block, then you would have to have some additional reads there. So if your answer was 1 here, it would mean your answer is 6 for this part. But if you didn't do that, the answer should be 4. So next question, file has a large number. Thankfully, I wrote it in powers of 2. IO blocks of content. How many index blocks are needed in total to store the pointers using an inode? You may skip the final calculation if you don't have a calculator. So remember, on an inode itself, it has 12 direct pointers, 1 indirect pointer, and 1 double indirect, 1 triple indirect. And also block size is 4096 4-byte block pointers. So we can figure out how many pointers we can put on a single block. So that would be 2 to the 12, which is 4096, divided by 2 to the 2, which is 4. That's our size of our block. So it means we can fit 2 to the 10 pointers per block. So these 12 are covered using the direct block. Or sorry, direct pointers. Only 2 to the 10 of these can be covered by a single indirect block, and remember, it would fill them up in order. So it would have 1 indirect, or 1, let's be very clear about this. This would be 1 single indirect block. And then I still have 2 to the 10 left over here, right? So I've covered those. I haven't covered all of those. 2 to the 10 left over. And then 2 to the 20, that can be covered by a single double indirect block, and then each of those would point to, so for the double, we'd have 1 double indirect block, and that would be full of entries if it can point up to 2 to the 10 things, and we'd be pointing to each of those entries would be pointing to a single indirect block, right? Because that's how levels work. And we would have, if they were full, we'd have 2 to the 10 of them. So we would have 1 double indirect block, and it would point to 1024. That's to the 10. Single indirect blocks. So just like page tables, we went down a level. So we've handled that. So now we have to handle the next to the 10 entries. So for that, well, we need one triple block. And if we're all good, we know we can fit to the 10 on a single indirect block. So at the lowest level, our single indirect block here would be full of to the 10 entries, be full to cover all of them. So I would need at least one entry here in my triple block to point to at least one double here. And then that can point to my single full one. So in total, the direct pointers don't count. I need one block for direct for my one level, if you want to think of it that way. So here's one from my single level. I need 1025 from my double level. And then I need 3 for from my triple level, because I have one block that needs to go through 3 steps. It could have a single entry pointing to one double block, so that would be like one L1 page table. And then here's my single L0 page table, if you want to think of it that way, full of entries. So in total, I need 1029. And yeah, basically what I did here is this 12, that was handled through the direct block. This 2 to the 12, I know through a single indirect block. Another way to write it is I could write the 11 as 2 to the 10 plus 2 to the 10, because that's how, you know, math works. So this can be taken care of by a single indirect block. 2 to the 20 can be taken away from a double indirect block, so I have to go through 3 levels to take care of the next 2 to the 10. How we figured out the strategy. So just the way it works, right? So the inode itself, how it works is there's 12 direct, so 12 direct pointers means we don't have to store them on a block or anything, right? They just point directly to data blocks. So this would be data block 0 all the way to data block 11, which would be the first 12, right? Because there's 12 direct blocks. Then it would have 3 pointers. Unlike page tables, this is basically one acts, if you want to think of it in terms of page tables, you can think of this as, hey, this pointer is just a single level. This is 2 levels. And this is 3 levels. And we'll fill them up in order. So remember, with page tables, the more levels we got, the slower it was, because it had more hoops to go through. Same idea with this. So the more levels I have, the slower it is. So I want to populate them in order. But unlike memory, where everything has to be treated the same, in this, if I don't need to use 2 levels, I just won't use 2 levels. So with page tables, if I have 3 levels, right, I only have 1 root page table, that's it. Here you can think of it as, hey, I have 3 root page tables, 1 for a single level, 1 for 2 levels, 1 for 3 levels, and I'll fill them in as needed. So if I have, for example, I have a 13th block here, well, then I ran out of room with my direct pointers, which are fast, so I need to have an index block here that can store up to the 10 entries, and then each one of those would point to data blocks, right? if I ran out of those, so I ran out of those to the 10, that means, oh crap, I have to use 2 levels. At maximum, I have 1 index block, which has to the 10 entries. Each of them, since it's 2 levels, points to another index block with to the 10 entries. And then each of those ones points to a whole bunch of data blocks. And then similarly for the triple one, although I'm going to run out of room here. So does that clear it up? Hopefully that's okay. I think that should be okay. And then last question says, assume a user ran the following commands. We moved, so move is just a rename. So we basically renamed a.txt to e.txt. So we would have 31 e.txt after that, and no entry for a.txt. And then if we do ln b.txt, that creates a hard link. New name is called a.txt, and it will refer to the same inode as b.txt. And up here, b.txt is 32. So it would be 32. And then the question says write the resulting inode name pairs for all the regular files in the directory. So we would have to also include b.txt as well. So it would be 32 b.txt. Oops, txt. Good writing. So that should be our answer. Seems to check out. So everyone okay with that? Seems to be a whole bunch of file system questions. All right, someone wanted to do the lost wake up question. Is there anything specific in that lost wake up question? Because the whole thing there is basically a data race with line 8, where it does not protect accessing the mutex. What would happen to the second line? Which second line? Okay, do I have it? Here, one sec. So which question was that from? That was 2013. Okay, 2013. Okay, so here is 2013 final for ECE354. So we are going to have a look at the Centerforce question. So the Centerforce question, and then we want file systems too. Okay, so this one says, given the struct and functions for a Centerfor implementation using a condition variable in the provided code, you'll identify and explain any issues. Assume the existence of Centerfor init, a function that initializes the Centerfor's mutex, condition variable, and value properly. Focus particularly on thread safety and correct Centerfor behavior. So should atomically post should atomically increment, wait should atomically decrement. The current value is 0, should just wait there until it can decrement it, so it should never be 0. So first one says, assuming the initial semaphore value of 0. So let's just say we have a semaphore up here. Its value is 0. The mutex is currently unlocked by any threads and is positive, which is our condition variable, which I like to just think about as a queue, is currently empty. So it says, describe a sequence of context switches between two threads concurrently running sem post. So we have thread 1 here. Let's give them different colors just for fun. So we have set up thread 1 to execute this function and thread 2 to execute this function. So describe a set of context switches between two threads concurrently calling sem post that could lead to unexpected output. Specifically consider the final value of the semaphore after these operations. So if this is working correctly, the final value, if we post it twice from two threads, should just be 2, right? That's how it should work. So first one is unexpected would be some value other than 2. And in this case, we don't have to worry about the mutex or really the condition variable because all we do is signal it and we don't use the mutex, which is kind of our problem. So plus plus value, we know that is going to load the value and then do an inc in a register, so into a reg, then we'll inc it and then store reg to value. So if we do this with our two threads, what might happen is thread 1 runs, loads the value 0, context switch to thread 2, loads the value 0, and now we're screwed. They're both going to increment them from 0 to 1, right? Classic data race. So that one should be fine with everyone, right? So both would write out 1, so our final value would be 1. That would be bad. So next one says, with the semaphore initialized to a value of 0, describe a scenario where lost wake up occurs due to concurrent execution of sem post and sem wait by two different threads. So in this case, let's reset everything. Well, we didn't really use as columns because it didn't really have to do anything. So in lost wake up, we need to put ourselves to sleep and then never wake up, right? So there should be some case where after these two calls, thread 2 is actually currently asleep and it should not be asleep, right? So what will happen? Bad thing that could happen is, well, eventually we know we want our final state to be where thread 1 is done executing, and in our lost wake up state, it should probably look something like this. So is positive just has thread, what I call it, thread 2 in it, and thread 1 is done executing, right? So in that case, well, first thing I have to do is I have to put thread 2 in the queue, and the only way it'll do that is just by calling wait. So if I know that, well, it will only put itself in the queue if the current value is 0. If thread 1 runs first, it's going to increment that value from 1 to 0 or 0 to 1, doesn't matter, and it's going to screw up. So lots of different things could happen here, but one that could happen, let's see if we can make it the easiest case possible, where thread 2 just starts executing. So it acquires the mutex, so it just acquires that mutex. So now thread 2 has the mutex. Oops. Thread 2 is the mutex. The current value is 0, so we would go into this loop. And then, well, right now if we waited, it would be in a queue, and then when T0 goes, then it would increment it, wake it up, and that would be bad because, well, that wouldn't be a lost wake up. So we can context switch right here. So context switch to thread 2 or thread 1 right now before thread 2 actually executes, and we can actually make progress on thread 1. So let's just assume, just to make it easy, this all happens atomically. So it will just load that summer value, increment it, so the value now changes from a 0 to a 1. Then thread 1 calls signal, which would wake up anything that's currently in the queue. Right now nothing's in the queue, so nothing wakes up. And then now thread 1 is done. And now we have no choice but to execute thread 2. So thread 2 is going to hit this wait, which will put itself in the queue. Also atomically give up that mutex. And now we have a lost wake up, right? It's not going to wake up. So no one's going to wake it up unless it randomly wakes up. So that's our case of lost wake up. So we okay with that? I think that should be okay for that question. And then, oh wow, we want more file system questions. Okay. So we want the file system question from this exam too. Hey, there's page replacement. All right, so another file system question. Assume a file system block size is our old faithful. Seems to be the exact same thing every time. So our block size is 2 to the 12. Pointer size is 2 to the 2. We have 128 byte inodes, so inode size is 2 to the 7. Yes, 2 to the 7. Then inodes have 12 direct pointers, 1 indirect pointer, 1 double, 1 triple. Analyze. Wait, didn't we do this one? Yeah, we did this one, right? Yes, we did. Okay, this was the one that was asked earlier and pasted in the chat, so we did do this one. Question 36 of which one? Yeah, so we did this one. Not sure what Q36 refers to. Does it count as being able to store? Oh, does it count as being able to store all the inode if there exists an inode 33, for example, despite there not being more than 32 inodes in a directory? So this is just saying, so remember when you did the file system, right? You had like your super block. Then you had like your group descriptor block or whatever. And then you had your inode table. This is specifically talking about kind of the inode table. And the inode table was basically just a big array, right? It was basically just an array of inodes. And if we want to figure out how many inodes we can store on a single block, this doesn't say how many inodes are available on our disk, right? So the number of inodes per block is just our block size, which is 2 to the 12, divided by our inode size, which is 2 to the 7, which is 2 to the 5. Or in other words, that's the only power of 2 I really remember other than 2 to the 10. It's just 32. So in our inode table, each block, so these little things I drew are blocks. So each block would be able to store 32 inodes. So the first block, considering it's just an array, that would be inodes 1, because they start at 1. Inode 0 is invalid. So this would be inodes 1 to 32. The next block would store inodes 33 to 64. The next one would store inodes 65 to whatever that is. 96, whatever. Go on, so on and so forth. So this question is saying, store all the inodes associated with this directory in a single block. So all the inode numbers here are within 1 to 32. So all the inodes would be stored on this block. So this would be stored on this block, this would be stored on, so they would all be stored on that block. If there was another one here, let's say we had inode 60. If we had inode 60, and let's just say we just called it hard.txt or something like that to make the question harder, well, that inode would be stored on this block, right? So then the answer would be, hey, we would need at least 2 data blocks for inodes, right? Yeah, so does that make sense? Yeah, so hopefully that answered that. And then there's another thing, 40. Oh, there's more questions here. Okay, cool. All right, so there's more questions here. So it says, what happens when you execute RMB? Is it possible for the file to be actually deleted? So in this case, no, right? There's 2 links to to inode 20. So if we RM something, that just removes the entry in the directory and decreases the number of links by 1. Doesn't actually remove anything aside from the entry in the directory in general. So if we removed or RM'd B, then inode 20 isn't deleted. We just got rid of this entry. So our number of links would just go from 2 to 1. And then the next question says, well, assuming if it was removed or is removed, well, it was. So this is saying, assuming what we did in the last question worked, what is the impact on c.txt and its associated inodes? And in this case, it would just be a broken link, but nothing happens to C itself, right? It just stays, it still refers to the name B. Just if we tried to open the file or follow it, it would have to look up B and then get the inode associated with B, which it wouldn't be found, and then it would just say file not found. So nothing changes in C. Next question says, if a file A is expanded to use 13 data blocks, are only 13 data blocks required for its contents? Explain the storage mechanism. So this is the same case as before. So given the inode, we can store 12 data blocks through the 12 direct pointers. That would have 1 data block left, right? So then if we have 1 data block left, well, then we have to go through that single indirect pointer, right? Which is a single level of page tables or 1 root page table. So this would be my pointer entry. It would point to a single index block because we're only doing 1 level. So this would be my index block. And that would be pointing to our entry, which would be data block, in this case, data block at index 12. So there's a question saying we'd actually need 14 data blocks in total. So there'd be 12 directly on the inode itself. Then we have 1 for the index block, and then that would point to our data block. So we're essentially wasting 1 because we need 1 index block here. Next thing says, I'm not sure what it says. Possible to store does it include the possibility of shifting inode order. Not sure. Possible to store just means would it all fit on the same block? See the wording. It's possible to store. Yeah, so just the is it possible to store is just all the inodes associated with the directory. Can they fit on a single block in the inode table? So if I wanted to be tricky or something like that, hey, go to that. Say we had entry, no, 34. Yeah, I guess they could all technically be on the same block, like they're all in a row, but it would start at block 1, right? Or inode 1. So, yes, they could all fit on a single block, but no, because only inodes 1 through 32 will be on the first block in the inode table. So it has to both fit and align. So inode, it would start with inode 1, so you have to take that into account. So yeah, so if it also contained, like I said, inode 34, 33, or anything like that, then the answer would be it is not possible to store it within a single block. You might be able to argue it. I would probably give you the mark if you just argued it. Because I could see how you could argue it. So if you could convince me of that from the question, generally we give you the benefit of the doubt. If it looks like you understand it, then yeah, that's fine. If you just said yes or no with no further explanation, then you're kind of playing with fire, right? So yeah, so if it had 34 on it and you said no and didn't elaborate further, then I don't know, what can we do? Yeah, the wording could be slightly better, but this was 2023, so generally if the wording is a bit wonky, it goes to you. So generally, if you can display your knowledge as part of the question, then it's all good. We err on giving you the grades as long as you demonstrate some knowledge with it. So if you write yes or no, if it's 2 marks, well, it said provide an explanation, so you had to provide an explanation. If it made sense, it was clear you understood what you meant, then we just gave you the marks. So wouldn't worry about it that much. Generally, if I have a question that's maybe possibly worded, also is accompanied with an explain. So from the explain, we can kind of figure it out. All right. Any other questions? Seems to be just a whole bunch of file system stuff, which is so I think that is everything now. Oh, wait, we have the last question. Oh, same idea here. So how many data blocks are needed if a file grows to fill 1040 block? Explains the storage arrangement of these blocks and the rationale behind that. So these are the data blocks, right? So 12 directly on the inode itself, 1 for an indirect block, which would store however many blocks we can fit, which would be 2 to the 12, that's our block size, divided by the pointer size, so we can fit 2 to the 10 pointers on each block. And then, so here, let's draw our inode. So 12 direct, that point to, wow, writing is bad. So these would point to 12 data blocks directly. Then for the single, this would be 1 level, so this would point to 1 index block. Then at most, this could point to that 1024 different data blocks. So this is 1024 data blocks. And this says, well, the wording here is a bit bad. I clean it up in later years. So in this case, how many blocks do we need to account for now? So this accounts for 1020 or 36 blocks through the direct and the sorry, the dogs are going crazy. I don't know if you can hear it. 1036 blocks through the direct pointers and the single indirect. So we need to use our double. So our double, just like with page tables, we need to have at least one index block as our root. So this would be like our L0 or L1 page table. And then it would need to point to another index block at minimum, right? Has to have at least one of each in order to do a translation. And then in this case, well, it only needs one entry here. And then in this case, it only needs 4 entries here to point to the remaining 4 data blocks. They would just be a bit slower. So our answer is, well, we have our 1040 data blocks, and then we also have to add in the index blocks we use. So it was 1 here for a single, and then 1 here, 1 L1, 1 L0 for our double. So we had 3 index blocks and then all the other data blocks. So these were our data blocks, and we needed 3 index blocks for it, for a total of 1043 blocks. All right, we also want to cover condition variables. All right, let me go back to my face so I don't accidentally spoil anything, although I don't think there's anything in my notes that technically spoils anything. And lucky or unlucky for you, I already forget what is on your exam because I have a very poor memory. All right, so oops, that is not the right thing. All right, so we want condition variables for the ECE. I'll just write it here. So this is the ECE354 2024 fall final. So condition variables. Consider the following code. So we have something with the last variable. We have 1 condition variable, 1 mutex. We assume they're initialized, and then a counter. Then we have a whole bunch of code we'll just ignore for now. And then we create 2 threads. So 1 thread is set up to run this run1 function. 1 is set up to run the run2 function. So, well, let's give them their IDs. So we'd have thread 1, or thread 0, sorry, set up to run this function. Thread 1 set up to run 2. So the question says, show a possible output of the code. If there's only one possible output, state so, otherwise provide one alternative output. So let's look at this. So if we look at the code, well, okay. First one, so it's in an infinite loop where we lock a mutex. They both lock a mutex, so knowing this, only one can pass this at a time, and we can kind of look at it and see what it's doing. So if the counter is, if we mod it by 2, if it's not equal to 0, so aka it is odd, we're going to wait for it. So basically, the condition variable in this thread is being used to signal if it's odd or even. So here, if it's odd, it's going to wait. Otherwise, it's going to print even, increment the counter, which is a global variable here. So it's just going to increment it. and then signal that, hey, it probably just changed it from an even number to an odd number. And then if the counter is greater or equal to the last value, then it unlocks the mutex, and then it returns null, so it just ends. Otherwise, it unlocks the mutex, so it just does one thing. Similarly for the other thread, just the condition here is just if the number is even, then it waits. So after it breaks out of that, so it's our normal while loop with condition variables, it will print out odd, and that is it. So looks like we might only have a single order here. So to convince us of that, we can just see what happens. So the current number is 0. So the current number is 0. So, well, if we have thread 0 execute first, well, it would go in here, get that mutex. So here, let's write out here. So if I'm following this cond, which is our queue, has nothing in it, mutex. Well, if I pass by this call, then thread 0 has that mutex. So it would go in here. If I context switch to thread 1, it would hit this lock call, can't make any progress, so I have no choice. I have to continue with thread 0. So in this case, it would hit while the counter does not equal 0. Okay, in this case, if we mod by 2, it is equal to 0, so it would skip over that, print even, counter is 1. Again, no other choice but to continue, increment it from 0 to 1, signal, nothing would be in our queue, nothing would happen. Is counter greater or equal to last value? No, so it would just skip over that, unlock it, and then we don't know which one could execute first. So if I rewound and said, hey, that didn't happen, we just had thread 1 execute first, what would happen is thread 1 would execute first, it would grab that mutex. Then in this case, thread 0 can't progress any further. Then we go in this while loop, we check counter mod 2. In this case, it would be not equal, it would be equal to 0 because the current number is even. So we would wait. And remember what wait does is it would put itself in its queue and then also atomically unlock the mutex. So it would unlock that mutex, and now we have no other choice but to execute thread 0. Thread 0 runs, well, it would actually, it would not release it from its confines in the queue. It would get the mutex. So thread 0 gets the mutex. It would check here. Oh, counter mod 2 is equal to 0 because the current number is 0. So it would skip over this. It would print, just like in that first case, it would print even 0. And then it would signal. So signal, again, would remove thread 1 from the queue. But just because it's removed from the queue, remember when wait returns, it needs to reacquire the mutex. So even if we pick thread 1 to execute right now, which we could, right, it's still in this wait call, and wait does not return until it can reacquire the mutex. Thread 0 still has the mutex, so we have no other choice but to keep on executing thread 0. It would check if counter is the last value. Okay, it's not. Then it would unlock that mutex. So it would do something like that. So it would unlock that mutex. Now, either we can continue with thread 1 or thread 0. If we continue with thread 0, just looking at this and getting a feel for it, it would sleep, it would wait, it would get itself set off in the queue because the current counter is not odd, it's not even. So it would put itself in the queue. So basically, run 1 is waiting for the number to be odd, or waiting for the number to be even, printing that it's even, incrementing it. Thread 1 is doing the opposite, right? While the number is even, it's sleeping, waiting for the number to be odd, printing it, and then going with the counter. So In this case, after getting a feel for it, you can just kind of see what's going to happen. You can kind of do the happy route. So in this case, if we keep on going with it, let's have our counter to here. So our counter increased to 1. So now if thread 1 gets the mutex, so it wakes up, it gets the mutex, then it would go here, okay, it would wake up, recheck, oh, the current counter, mod 2, oh, it does not equal 0, so it would break out this while loop, then it would print odd 1, increase that counter to be 2 on this line, signal, nothing's in the queue, check is counter equal to or greater than last value, oh, it's not, so we can continue going. Gets kind of boring. Do you want me to continue, or is that fine to figure out the rest of it? The solution should kind of guide you through it. But that's kind of the general feel for it. So in this case, it's just going to do what it had, or, well, there's only one possible solution, so it's going to kind of ping pong between the two threads. So it's going to go even 0, odd 1, yeah, and of course I'll be on Discord too, but it's just going to ping pong. It's going to go even 0, odd 1, even 2, odd 3, and then it's going to end. But yeah, I'll be on Discord as well through, up to your final exam. I'll have to drive in very early on the 30th, but I should be around pretty much all tomorrow on Discord, minus eating and possibly taking a nap. So any other questions, or are we all good for not tomorrow, 2 days from now? And this is everyone's last exam, so yeah, you have nothing else to study for but this now, and it's almost over. So any other last minute questions, comments, concerns? Your exam format, I mean, generally pretty similar to the latest one, which they're all kind of similar, but closest to 2024 ECE353. Again, of course, your questions are going to be slightly different. Same setup. The weighting is a bit different. Well, like the weighting's more or less the same, but I think you have one less question, but it's worth more. The number is about the same as far as what I remember. It's about on par with that exam. Hopefully there's no problems with it. It's stressful both for you writing the exam and for me watching you write the exam, because if anything goes wrong, that's not great. Yeah, practice the clock. That's, that should be on it. Otherwise, I think I dropped most of the hints in the course recap one. Oh, I have a quick question for virtual memory. The SEP is good. It's just the actual translation. So 2023, this final. Okay, here, let's start it off good and you can let me know when we are all good. Oops, should look at me. So we have so is that the 2023 ECE353 final. All right, so this should be the exam. So winter 2023, let's go here. Oh, there's page replacement. All right, virtual memory. So hey, this still looks like the same thing as yours. So we have a 12-bit virtual address, 8-bit physical address, page size of 16 bytes. Again, I always like to write out powers of 2, so that is 2 to the 4 bytes, and page table entry of 1 byte. Our page table entry has the following layout, where the physical page number, PPN, or physical frame number is the most significant 4 bits, and the permissions are the least significant 4 bits. So it also says that, hey, our page table entry is 1 byte, so this is our 1 byte page table entry, which is 8 bits. All right. So is this the one that has the error? So it says how you read physical memory is, this is basically, row column. So you add the numbers, and each of these are 2 hex digits, so that represents a byte, right? 1 hex digit represents 4 bits. So gives an example. So the byte at address, in this case, 24. In this case, you match the row and the column. So 20 plus 4, that would be here, that would be 3F. And this one doesn't have an error like other ones have. So yeah, is virtual memory even fair game? We did that twice. So NSI seem to have a problem with virtual memory. Generally, I ask virtual memory questions if a virtual memory question is done poorly on the midterm. So you be the judge if there is a virtual memory question. All right, so first one. How many bytes are needed to store a single level page table if we need it? So remember, in this case, we have 12-bit virtual address. Well, we know from our page size we need 4 bits for the offset. And then our virtual address, the rest of it is always going to be a VPN. Whether or not we use it in levels doesn't matter. It's always going to be the rest of it. So we have 8 bits for our VPN. So if we use the single level page table, we need to have an entry for every single virtual page number. So we would have 2 to the 8 virtual page numbers to keep track of, and then each entry is 1 byte, which is just 2 to the 0. So that's our page table entry size. If it was larger, we would have to multiply, right? So in this case, we just need 256 bytes. All right. Next one is, all right, so minimum level page tables, this said it was fine. Next one is for 11. So it says we're going to translate virtual address 1, 2, 3. So with all of them, this is with our multi-level page table, right? So with our multi-level page table, we had 4 bits offset, and this is our 8 bits VPN. Previous question has us doing 2 levels of page tables. So in this case, for 2 levels of page tables, we'd have 4 bits and 4 bits. So this would be our L0 index. This would be our L1 index. So if our virtual address is 1, 2, 3, where this is in hex, that means, well, conveniently it maps up. So each hex digit, or hexit if you want to call it that, is a 4 bits, so it kind of lines up nicely with this. So in this case, this would be hex 1, hex 2, hex 3, or decimal, they're going to be the same thing. So this is basically asking you to just put them in each category, right? So in this case, the offset, boom, we have it because the offset is this, like we said before, right? So this is the offset that we're actually using for this question, or for this virtual address. So it's offset to 3. Next one just says what's the index of the highest level page table. So the highest level is L1. So that'd be this one. And then the lowest level, which is L0, would be this one. So it's just that. And then for doing the translation, how we do that is, well, it's set up that our highest level page table is at ppn 2. So in here, ppn 2, and we figured out that each page table has 16 entries. So that means in this case, if it's at ppn 2, it means these 16 bytes are like our entries. Here, let me give a closer shave to that. So these 2 columns of addresses, there's 16, in this case 16 bytes, so we'll treat them as 16 PTEs, and this is our L0 page table. So our index that tells us to go at is, for this L1 page table, is 1. So we would go over, this is index 0, this is index 1. So this would be our page table entry here. So our page table entry would have 1F, and then knowing our layout here, well, 1, that means the ppn would be 1, and then all the bits, F is just 111, so they would all be valid. So that tells us, hey, well, it's valid, so that means we're using physical page 1 as our L0 page table, which would be, let's use a different color, which would be these 16 bytes, right, which is page 1. Then we use our L1 or L0 index, which would be 2. So again, this is 0, this is 1, this would be 2. So again, that entry would mean it's physical page F, and then the other F here means it's valid. So that's our final translation. So that's good. So we don't have to translate the offset or anything like that. And we just substitute that VPN, which was 1, 2, with the PPN after we find it. So our final physical address would just be F3. So this was, this was from the PPN that we've looked up after 2 levels of page tables, and this is just the offset that we don't change. All right, so hopefully that got you. Oops. Don't know. Oh, that's the other course. All right. So, any other last minute question, comments, concerns? Otherwise, I will sign off and then monitor the Discord. All right. Sounds good. So, let's do this. All right. So, good luck on Monday. Wednesday. Last exam. Bright and early. I will see you on the 30th. Again, I'll be on Discord to answer any questions or anything like that. And good luck. Remember, pulling for you. We're all in this together.